Hey everyone, and welcome. Today we're going to dive into one of math's coolest shortcuts, the binomial theorem. Seriously, this thing is a powerhouse for crunching huge calculations. And the craziest part? It's all hidden inside a super simple pattern. So let's unlock it together.
All right, just picture this for a second. Have you ever tried to multiply something like a plus b by itself 12 times? I mean, really think about it. Multiplying that out by hand would take, well, forever. And you'd make a ton of mistakes along the way. There's just got to be a better way, right?
And hey, even something that sounds simple, like a plus b cubed, gets messy fast. You know the drill. Multiply the first two, you get that trinomial. Then you got to multiply that whole thing by a plus b again. Yeah, it works, but man, is it clumsy. And you know, this is exactly the kind of tedious problem that mathematicians just love to find a beautiful solution for.
So instead of just grinding it out, the brute force method, let's be a little more clever about it. The real solution here is to step back and look for a pattern. There's almost always a pattern in math, right? Let's start small and see what we can find.
Okay, so here are the first few expansions. For a plus b to the power of 1, it's just a plus b. Easy. To the power of 2, you get a squared plus 2ab plus b squared. We all remember that one. Then for the power of 3, it gets a little longer. Now, just looking at these all lined up, do you start to see anything? Any kind of pattern jumping out at you?
You know, if you really look closely, a couple of things become pretty clear. First, check out the powers of a. They start high and go down with each term. And at the same time, the powers of b do the exact opposite. They start low and go up. Pretty cool. And here's another thing. If you look at any single term, the two powers always add up to n, the main exponent. But what about those numbers in front, the coefficients? That 1, 3, 3, 1? They seem to be following their own little secret code.
Well, that secret code has a name, and it's one of the most beautiful things in math, Pascal's triangle. This is the key. This is how we crack the code for those coefficients. And the best part is, the rule to build this thing is so simple. You just start with a 1 at the very top. Then every new row starts and ends with a 1. And every other number in between, it's just the sum of the two numbers right above it. That's literally it. It's that easy. And look at this. This is where it all connects. See that row for n equals 2? The numbers are 1, 2, 1. Where have we seen that before? Those are the exact coefficients for a plus b squared. And the next row for n equals 3? 1, 3, 3, 1. The coefficients for a plus b cubed. Boom, we found it. We found our shortcut for the numbers in front. Okay, so Pascal's triangle is amazing, right? It's a great visual shortcut. But what if you needed the coefficients for, say, a plus b to the power of 100? Are you really going to write out 100 rows of the triangle? No way! We need something more powerful, a formula. And that's where we get to the theorem itself. So before I show you the full formula, there's this one little piece of notation we need to get our heads around. It looks like NCR, and we read it as n choose r. This is called the binomial coefficient, and it just answers a really simple question. If you have n things, how many different ways can you pick r of them? That's all it is. Like, if you have 4 friends, how many ways can you choose 2 of them to go to the movies? That's just 4 choose 2. And here it is. This is the big connection. It turns out that every single number in Pascal's triangle is just one of these n choose r values. So that row for n equals 4, you know, the 1, 4, 6, 4, 1, that's literally just 4 choose 0, 4 choose 1, 4 choose 2, and so on. This is just the formal mathematical way of writing down the pattern we already found. It's the same thing.
All right, drum roll please. Here it is, the binomial theorem in all its glory. This is the complete recipe. It brings everything we've talked about together. It tells you that for any term in the expansion, the coefficient is just n choose r. The power on a is n minus r, and the power on b is r. It's the whole shebang, all wrapped up in one elegant formula.
And we can actually zoom in on this theorem and pull out an even more useful little tool. We call it the general term formula. And honestly, this is what makes the whole thing so incredibly powerful. It lets you find any, and I mean any, single term you want from an expansion with total precision without having to write out all the other terms. It's like a surgical strike. All right, that's enough theory for now. Let's get our hands dirty. Let's see how this formula can just completely demolish a problem that would be an absolute nightmare to do by hand. So here's our challenge problem, and it's a doozy.
we need to find the coefficient of the x to the power of 11 in the expansion of this thing. Now, trying to expand this out 12 times, no. Just no. That's out of the question. But with our new general term formula, we can find exactly what we're looking for. Okay, we just need to follow the recipe. First, we identify all the parts. Our n is 12, the a term is x cubed, and the b term, and don't forget the negative sign, is negative 2 over x squared. Next, we need to figure out which term gives us x to the power of 11. So we set up a little equation using just the exponents. The a part gives us 3 times 12 minus r, and the b part gives us negative 2 times r. We set that whole thing equal to 11. Do a little algebra, and we find that r equals 5. Perfect. Now we just plug that r equals 5 back into the coefficient part of the formula.
And there we have it. The calculation is 12 choose 5, which works out to 792, and we multiply that by negative 2 to the 5th power, which is negative 32. Put it all together, and the final answer is negative 25,344. I mean, think about that. In just a few quick steps, we found this one specific number hidden deep inside a crazy massive expansion. That is the power of this theorem.
So we started with this really tedious problem, right? Then we found a beautiful visual pattern, and that led us to an incredibly powerful formula. And, the binomial theorem isn't just for algebra class. It's super important in fields like probability and statistics. Which kind of leaves us with one final big question to think about. Now that we've seen how this pattern works with numbers and letters, where else in the world might a pattern like this be hiding?